Myself, Dr. Saurabh Devna. Today's topic is the calculation of the unsymmetrical fault. In the unsymmetrical fault, you have seen that there are three separate components. That is the positive sequence component, negative sequence component, and zero sequence component. Here, the sequence component is applicable for the both current and voltage. I have already discussed in the last class. So there is the presence of the voltage, similar different voltage or current. Obviously, there is the presence of different impedance for the three separate sequence. Here, the positive sequence impedances is denoted by Z1, negative sequence impedance is denoted by Z2, and zero sequence impedance is denoted by Z0. Now, there are some assumptions before making the analysis of unsymmetrical fault, that is the LL, LG or LLG fault. First one is the generated EMF is always positive sequence component. That is the generated EMF is always balanced in nature. There is no amount of current flowing other than the fault. The impedance of the fault is zero. That means that where the fault is occur, the total impedance is being zero. And R phase is taken as the reference phase for each analysis. Now we are going to the single line to ground fault. Here, this is the generator. The generated EMF is ER, EY, and EB. And here we are assuming that R phase is directly grounded. So, as per the assumptions, there will be no current flowing through the Y phase and B phase. That's why IY and IB is being zero. Now, you are simply apply the KVL to this network. That is the ER is equal to IR. Here, IR is the fault current for R phase. So this fault current is summation of the positive, negative and zero phase sequence. So I0 Z0 plus I1 Z1 plus I2 Z2 plus VR. Okay, so this is the value of the ER. Now the value of the I0 is 1/3 of IR plus IY plus IB. Here in this case IY and IB are being zero. That's why I0 is 1/3 of IR. I1, the value of I1 is, this is the formula, 1/3 of IR plus alpha IY plus alpha square IB. That's why these two portions, that is the IY and IB are being zero. This portion is 0 and this portion is also 0. That is the I1 is 1/3 of IR. Now, similarly, I2, that is the negative phase sequence component of the current, is also 1/3 of IR. Putting this value and you have get this value of I0. Here you can see that I0 is equal to 1/3 of IR. Putting this, that is the IR is equal to 3I0, 3 of ER divided by Z1 plus Z2 plus Z0. This is the final equation you have derived. In this equation, you can see that there is the EMF. This is the EMF and this is the impedance. That is the 3ER. 3ER the generated EMF. This is the 3ER. And the impedances are simply summation where they are connected in the series. That's why Z1, Z2 and Z0 are connected in the series. And this is from the network where the fault current IR is flowing through this network. Okay, this is the analysis of single line to ground fault. Now, next topic is double line fault. In this case, we are assuming that the generated EMF for R phase, Y phase and B phase are ER, EY and EB respectively, and Y phase and B phase are being short circuited. Here you can see that the VB is equal to VY because two phases are short circuited, and in this case there is the only one generated EMF, and this generated EMF is connected to the two parallel impedance Z1 and Z2. So you are getting the value of the I1 is equal to minus I2 because the direction is same. So that's why we are putting the minus, and ER divided by Z1 plus Z2. This is the simplified analysis of double line fault. Next, double line to ground fault. Here Y phase and B phase are short circuited. That's why IR is 0, and the realization of the figure is this is the generated EMF ER. Okay, and where in this circuit you are wishing to calculate equivalent value of Z, that is the Z1, and Z2 and Z0 are parallel. So you have put this and simplified this, and you have get this formula for the double line to ground fault. Thank you.